All right, so we're going to apply the integral test for the infinite series given in part B, but first we have to write the sum in terms of an infinite series in the sum notation. So we can write this as like n starting from 2 all the way to infinity, ln n over n. Okay, so this is the n term of ln n over n is the n term of the infinite series. Sum starts from 2, that's okay. Okay, so that means I'm gonna try to check all these conditions for x greater than or equal to 2, but let me just write also that an equals fn, that's ln n over n, and let me just use the x notation here. So ln x over x is greater than or equal to 2. So for some reason, if x equals 2 is a problem, I can start the sum, I can start the integration along the way from 3. That's okay. But for the time being, let's check if f is positive. Well, first of all, x is positive, and in fact, x is greater than or equal to 2. The bottom here is always positive, okay? And ln1 is 0, and anything that you plug in for x bigger than 1 makes ln positive. So I can put a check mark here that ln x over x is positive, or x is greater than or equal to 2. As well, ln x is continuous in its domain, which is open interval 0 infinity. And x is continuous, and ln x over x as a ratio is continuous as long as the bottom is not 0. In other words, as long as x is not equal to 0, f of x over x is continuous. But again, we're safe because x is greater than or equal to 2. F of x is going to be continuous for x greater than or equal to 2, x greater than or equal to 2. We're safe. And number 3 is f a decreasing function. Well, we can't say it right off. We have to check f prime. And using the first derivative test, if f prime is strictly negative for certain x's, hopefully for those x's, then I can go back and then check that f is decreasing. So why don't we check f prime? All right, so we have the quotient ln x and x, quotient of that. So we're going to use the quotient rule from Calc 1. So it's the derivative of the top, which is 1 over x, times the bottom, minus the top times the derivative of the bottom, which is 1, all divided by bottom squared. Okay, let's simplify this. So it's 1 minus ln x over x squared. Well, here we consider x's to be greater than or equal to 2. You can go ahead and check that since ln 1 is 0, you can go ahead and check that this is negative for x is greater than 2. So here, there's just a quick comment here. If you start x to be x from 2, ln 2 is 0.698 approximately. So 1 minus of that is going to be positive, okay? So you don't want x to start from 2, but we can start it from 3 because ln 3 is 1.98, and ln is an increasing function. So we are safe saying like I can go back and then change this to that. So I can also change this to that. Okay, all right. So we're safe with x is strictly greater than 3. So all I'm going to do is to check now the integral 3 to infinity of ln x over x dx. Okay, so if this is convergent, that means that if this is convergent, as a conclusion, the infinite series version of this is convergent. So the series n starting from 3 all the way to infinity is convergent. And if you want to start the sum from n equals 2, well, n equals 2, as you see, it's just one number added to the sum for which n starts from 3. And ln 2 over 2 is a finite number, so any number added to another finite number in the case of convergency is a finite number. Okay, so let's put a check mark here, and then now I'm checking integral from 3 to infinity ln x over x dx. All right, as always, I don't need to worry about the limits at this moment. So this is an improper integral, obviously. So why don't we just look at the indefinite integral without the limits, right? So, well, we're going to use the, I think in this case, so again, this relies on our integration skills. So I think ln x has a derivative of 1 over x, and 1 over x is already there. Why don't we call u to be ln x here, so that du, it's u substitution problem essentially. Du equals dx over x, okay? 1 over x dx in other words. So this integral is turned into u du type integral, and we know how to integrate this. This is u squared over 2 plus c, but I don't need to worry about plus c because I'm going to use it for the calculation of this integral here. So u squared over 2 is ln x squared over 2. All right, so this was a side calculation. So I'm now back to this integral. So this integral is equal to ln x squared over 2 from 2 to infinity, but this infinity limit is written when it's plugged in, and it's going to be written as written in the limit sense. So in other words, I'm going to write it as like limit as b approaches infinity, ln b squared over 2. This is me plugging in the upper limit in the limiting sense, minus ln 2 squared over 2. Okay. One thing that we know about ln function, ln is an increasing function, and ln infinity is going to be infinity. So unfortunately, this integral diverges because this is a finite number, and then this is already infinity. So this diverges to plus infinity, and in turn, the conclusion here is that so this is divergent. I can go back to the description here that I can conclude that this series starting from n equals 3 is divergent. Okay, and if I start this sum from 2, that's going to be still divergent because it's me adding one extra. It's me adding one extra term into the game. That's not going to change anything. So I can go ahead and conclude that this series is divergent. Right? This is us using the integral test, showing that this is divergent. This integral is divergent. That implies that this series is divergent. Okay. The series for n starting from 3 is divergent, and therefore this series has to be divergent. All right.